Hello YouTube. Let's have another look at the chess program. And what I want to do today is to continue looking at ray attacks, but today I want to look at implementing blocking of ray attacks. So if you recall, last time we implemented the following. Where for each point we can calculate various ray attacks going in some direction. But now what we want to take into account is, what if you have a piece on this location that I'm showing right here? What if you have a piece here? Well, in that case, this one should not be active. This should not be marked as a valid attacking square or a valid square to move to for this piece. Furthermore, if this piece was of the same color as this original piece, then we shouldn't include this one either. But for now we will ignore that. We'll assume that you can always move to this square even if there's a piece there. So to do that, we need a way to indicate whether a square is occupied, and to do that we use bitboards. So I'm going to first, just for convenience of running this stuff, I'm just going to comment this out, and then I want to show you how I want to indicate that a board is a square is occupied. So let's say we want to implement this blocked rays, let's say, so let's write a test function for that. And to do this, I need some way of indicating the occupancy of the squares. So let's make a variable called occupancy. And then let's say the first 16 squares are occupied. Then I would just set those 1 bits, or those corresponding bits, to 1. And then that will indicate that those squares are occupied. So let's have a look how that looks. Then we should be able to just say this, and we don't want any marks. Let's run that. Right, so here's the output, and as you can see, all of the first 16 squares are marked with 1. So we can also say, let's take the last 16 squares, and I think it's from 48. What happens if you do that? There we go. But let's make a little bit more of an interesting board. Let's say if I is 5, then we don't want anything there, and then we also add 1 at this location. Oops. Let's say 6. No, what do I want to do here? No, that's fine. And like this. Okay, so a little bit more is happening now. So now what we want to do is, let's say we add array, and let's just do this. And then we also plot that ray on top of the rest of the bitboard. That didn't work as well, so let's put it on 4th row and the 7th column. Okay, and let's not do the north way, let's do northwest, just because it's a little bit easier to see. And then we can also mark the starting point. Compile. Okay. Great. Actually, let's put it down here. So now it almost looks like a real chess position where you have kind of fianchettoed your bishop. You put it here and then you're looking at one of its possible attack directions. Now, if you recall before we did this, there was a piece here. So what we want to do is calculate this blocking thing. And let's get started on that. So I'm not sure it will stay like this, but let's say we want a function that calculates a blocked ray. So we're going to need the ray itself, represented as a bitboard. So I guess we can put bitboard here. Then we will also need the ray family for reasons that will become clear soon. And we will need to know if it's a forward ray. So basically, if I have this ray here, let me draw it again and comment this out. Oops. If I have this ray, then I want to find the intersection of the ray with the occupancy. So let's try to calculate that. So here's the intersection. So that's where the ray hits a square that's already occupied. And to find the blocked ray, I want to remove everything after the first intersection. But depending on which direction the ray is going in, it will mean different things. So in this case, you can see it's the least significant bit. But if the ray was going left, maybe you can imagine that it would instead be the most significant bit. So depending on which type of ray it is, we have to look for the least or the most significant bit. I hope that makes some kind of sense. And we will of course also need the occupancy. And it should return bitboard, let's say. So, the forward ray, we do something, else we do something. So let's start with this interpretation. So first I want to find where the ray hits an occupied square. And then, as I said, we want to find the index of the least significant. Well, we already defined a function for that. It's called overlap. So, no, it's called bit scan, sorry. But actually, it assumes that there's only one bit set, which is not so good. So we can use a trick where we just isolate the least significant bit, and this is some bit wizardry which I can go into later. But basically, this is a way to get the least significant bit, And then it doesn't matter. How many bits are set. So let's just write a test for that. So you can see in the test before we only had 1 bit set, but now we can test that it works also with multiple bits. Okay, and here you can see the function. So we loop over all indices from 0 to 1. We set that bit, and then we also set some bits above that where we set them if this boolean is true. It's not really important. You could also just use a random generator. But let's try to run that. Then we need to go in here and say to do, and bit scan works if highest bit is 1. Failed. So let's have a look at that. Okay, so the problem is it's marked as should panic, but now because we generalize the function so they can work for any number of bits set, this doesn't panic anymore. So I will remove that. And now if I run the test, it works. Okay. So let's get back to implementing this guy. And once we have the index of the lowest, the first intersection, basically, we want to find the ray after that. So actually, we can do like this. We can move this out. That one can go there, and then bit index goes here, and we'll leave the other one as a to-do for now. But then we want to find the ray after that, which is given by the ray family at that index. And then the result is the exclusive OR of the ray and the ray after. So everywhere where they overlap, you get 0. And that should do it. Let's try to plot that. So first let's plot the ray we're interested in. And let's also, okay, I should write a function for this. Have to do like so. So first we print the board. Let's get this out of the way. Then we calculate the blocked ray. I call it blocked ray attack. And we need the rays, northwest rays index. We need the family of rays. It's a forward ray, and we need the occupancy. And then we just want to print that again. And it did not work because we have to say, give me the functions from utilities. Also did not work because, come on, this guy has to be a reference. And let mute. Can remove it. Just remove the warning. Okay, here we go. So first we have the occupancy. Then we have the ray we're interested in. And we can see that at this point, like if you go 3 down from the upper corner, 3 and let's say 2 down and 2 out. 2 down, 2 out. It hits something, but before that it doesn't hit anything. So then we get the blocked ray as this, which is exactly what we would expect. So we hit something here. That means this one and that one should be removed. So 2 down, 2 out. We hit something. The rest is gone. So that's exactly what we want. Now the problem, the thing we still need to implement is, let's say we instead go southwest, and we let's say we go to row 8 instead, and let's just try to run this, see what happens. So now we are starting at this point. Yeah, good enough. Let me add the point over here. So we're starting at this point. It should go southwest, so like this. And finally, it should hit a point here, and then the last one should be removed. So let's see what happens. Goes down as expected, and then we get some kind of weird result. It's definitely wrong. It's like it's hit the edge and bounced off. Excuse me. So the problem is that this is a kind of a backward ray. So to see what that means, let's do this and plot occupancy and this ray. So anyway, they intersect here, and what we want to find is the first intersection, which is this, but we do a bit scan forward on this thing down here, which means we get this index. So we do a bit scan forward, so we get this index, and then we do an exclusive OR on the ray after, but the ray after is okay, so that's why it was wrong. Here we go. There was something that didn't make sense to me. So we hit this point, and then we say the ray after, we do an exclusive OR, but the ray after is empty because it's going southwest, but there's nothing, it's just going out the board, so the exclusive OR, like the blocked ray, is unchanged from the original ray. So what we need is a bit scan backwards. So let's implement that. Now, you remember we did some fancy things to do the bit scan forward. I'm not going to bother with a super fancy thing now. So basically, if you have a bit string with 1 bit set, let's say it's like this, then this is of course equal to 1, 2, 4, 8, 16. So it's 16, also known as 2 to the 0, 1, 2, 3, 4. So you can see what I'm getting at. The index of this number 1 is then, index of 1 is equal to the logarithm base 2 of the number. Let's try it like this. Now what happens if you have some more things? Well, then it's 18 in this case, which is 2 to the somewhere between 4 and 5, so like 4.2 or something. So then if I do the log 2 of that, I get 4.2. And the point is that this number that I get out of this will be between 4 and 5. And the only time it will be 5 is when we go to this one. Other than that, it will be for any other, any of these bits, however many you set, it will always be less than 5. So a trick to get the most significant bit, do the bit scan forward, is to first cast it to a float, so we can call the base 2 logarithm, then take the floor, and then we have to cast it back. And we can also write some tests. I will just quickly do that. Okay, and here is the test. We just set the highest bit, and then we set some random bits below that. We call bit scan backwards, and we see that the result is equal to what we expect. And as you can see over here, it passes. So the implementation is correct. Now we can go up and implement the other branch, where bit index should be bit scan backwards of the overlap, and the rest should be unchanged. Okay. Bit of a crazy formatting. And now when we run the test, it doesn't work because why not? Did I type it wrong? Bit scan backwards. There we go. And then we have to change it down here. Now, so we start with array, we calculate the overlap, and then we remove everything after. So clearly that's wrong. Let's see what went wrong. Okay, very interesting. Okay, let's try to print the overlap. So sorry, let's get the what the bit scan backwards returns. So bit scan backwards of this thing, and then we just mark that. No, let's just do like this. And it did not work because I forgot semicolon, and it did not work because I forgot a comma here. Okay. So it correctly finds this one. And then what's the problem? So let's try to print that array. Raise, southwest, raise, add that one. we find the correct one. This is correct. Then why isn't it blocked? Ah, okay, so here's the problem. We have to remember that we have to tell it it's a backwards ray. So let me remove all of this now. Okay, and now the ray is correctly blocked. So that's it for now. That's implementation of blocked ray attacks. Probably it will not look like this in the end when we calculate when we implement our final move generation code, but it's good enough for now. And I guess next time we will look at knight moves. Why not? Or pawn moves or both. But see you.